Video series. We're moving on in the textbook Dive into Systems to section 4.4, Binary Integer Arithmetic. We have talked about this a little bit in maybe 2 videos ago or so, but I didn't talk as deeply as we could about carrying, so I wonder if maybe we're going to get into that with some depth. Keep in mind, I guess, some of the point here, well, okay, so let's just imagine that we're going to add 2 bits, or, digits, right? Binary digits. And so, but we know that what we're sort of wanting to do with however we handle this is to align a whole bunch of digits so that, you could have a 1 0 1 1 0 and a 0 1 0 1 1 or something like that. For now, let's just focus on unsigned, right? So this is, this is the 2 to the 0 place, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. So it's that very simple thing. Because we don't try to account for signs, then this reads very much like a standard binary number. Okay. And the idea is that, you're going to add some digits, so maybe that's just a 1. That's fine. But then you're going to add these 2 digits, and you're going to get a 0 in its, specifically in this coordinate. You're going to get a 0 in the units place, so to speak, and you're going to want to carry a 1. Well, what that must mean is that, for all except the very first column of digits, you really, right, whether you write it explicitly or not, there is going to be some kind of a carry in, right? So there's not just the 2 digits, but there's also a potential carry. And so that's what we're trying to kind of, model here, is that you've got digits, yes, but each one is also going to have a carry. Now, especially when you're adding, we will probably see that when we move on to subtracting, we're actually going to deal with these things, we can sort of deal with subtraction by having both a carry in and a carry out. When we're adding, there's never a carry in, but we'll see how some of these things sort of change if we try to sort of use these components to accomplish subtraction. But anyway, so you have inputs, which are your 2 digits, and a carry in like this. So you think like, okay, so I've got digit A is 1, digit B is 0, and the carry in is 1. So those are like all of your inputs, in a sense, to this result that's going to go down here. And so then there's the output, and the output is itself the result, the 1's digit, whatever goes here. But also keep in mind that if there is, overflow in a sense, then it needs to carry to the next coordinate. So the results are not merely the thing that goes in this coordinate, but also whatever might carry to the next coordinate. So that's all parts of your output. Okay. Now, when performing subtraction, a straightforward way to perform subtraction, say that you're going to compute 7 minus 3, is if you have an operation to negate a number, then you might as well simply resort to addition with the negated number. Those are equivalent computations. So as long as you can take a single number, negate it, then that is effectively all you need for subtraction. So let's say, now, and by the way, if you are working in unsigned integers, then there is no way to represent negation, at least not like, sort of as it would be interpreted in bits as an unsigned integer. Like, we know that unsigned integers are not supposed to represent any negative numbers. And so in that sense, there is not negation. But we can still use the 2's complement concept to simulate subtraction, right? So although, let's say that we were going to take the number 7, and let's just stick to, let's say, 2 bits, because with 7 and 3, we only need 2 bits to represent, 3 bits. So 7 is the number 111. 3 is the number, 011. So this is 7, 3 is 011. And so let's think about what we would do to subtract 7 from 3 using, these things, and especially trying to just sort of reduce this to a negation. So if we use the 2's complement concept of how you negate a number, we would bit flip, get 1, 0, 0, add 1, so we get 1, 0, 1, and then we add, and we get 1, 1, 1, 1, 0, 1, add, get 0, 0, 0, and then 0, 1. So now let's think about how we could possibly accomplish subtraction. Now, there is, an algorithm that we're familiar with subtraction, but it turns out that trying to implement that algorithm for subtraction, where, basically, you have 5, 6, 7, minus 9, 8, and you try to subtract these. So what do is you say, okay, I'm going to, 7 is smaller than 8 here and here, so let's borrow 1 from here, call that 5, but carry the 1, and so we call that 17, and it gets very messy and ugly. And trying to implement this algorithm in hardware with, binary numbers is not an easy translation. It turns out not to be a good idea. So we're not going to try to do that. But instead, what we can try to do is if we could simply take a number and negate it, right? If we could work with negative numbers, then we could take 7 minus 3, that's the goal, to subtract 3 from 7. And if we could perform the separate operation of negation, if we could take the number 3 and in fact just transform it into negative 3 and then take the operation of addition, which we already know how to do, that will result in an equivalent value. Now in 2's complement, we have already talked about how to negate a value. And since we've also, so in any case, so let's go ahead and think about this using the 2's complement system. So we have the number 7 represented as 0, 1, 1, 1, using only 4 bits. And if we use we're going to subtract the number 3 is represented as 0, 0, 1, 1, then we would like to negate 3. We've talked before about how that is effectively the same as bit flipping. And then we want to add 1. Now, the thing is, right, because of the whole carrying system that we've been talking about, well, if the unit's digit has a carry in, just like every other digit, then, okay, we could basically bit flip and then add 1. That there's no reason why we couldn't do that, but it is a little bit easier, and in hardware, it's, if we could just exploit that carry in to say that, well, when we're subtracting, what we do is bit flip and then set the carry into 1, and that accomplishes the same result with fewer operations, I guess you could say. So that is the strategy that we use to subtract numbers when using 2's complement and exploiting the carry in. So let's just trace how that goes with 7 and 3. So we're trying to do 7 minus 3. We bit flip and we set the carry into 1. Now, when we compute using the usual methods, then we, add this column with the carry, right? A carry is coming into this column, so that becomes a 0, and then we carry again. So with a carry here, then you get a 1 in the digit, and then you carry again, you get a 0, and there's a 1 in the carry out. Now, what you sort of want to appreciate before worrying about the carry out, which gets truncated, is that the truncated result is, in fact, the right result. And this is, somewhat due to the fact that if you think about how we said the numbers work, right? Again, let's make a number line where that's the number 0 and this is the number 1, and we know that this is the number negative 1. Keep in mind that if you take this, you add 1, it has a carry out that gets trunked. But, and keep in mind, right, again, I want to emphasize that this is the number 1, this is the number 0, this is the number 1, negative 1 over here. But, right, keep in mind that, the truncation is not intrinsically a problem because we are choosing to represent these numbers in a way that is, not exactly how you might be used to the numbers being represented and behaving. So when you add 1 to -1, you get a 0 in every single place and then a carry out at the end, and that carry out simply gets truncated, resulting in 0, and that is in fact exactly the right result. So what is important to kind of recognize here is that especially when it comes to that final bit, if the carry in is 1 and the carry out is also 1, as it was in this example and also as it is in this example, because keep in mind that the carry in was 1 and the carry out was also 1 because it flowed into the next digit, so to speak, or it would if there was one. Anyway, the point is that when the carry in is 1 and the carry out is also 1, then in fact you get the right result. Notice also, by the way, that if you had a carry in of 0 and a carry out of 0, like, for instance, if you look at going from 0 to 1, when you add, and especially if you pay attention to that final digit, it has a carry in of 0, because nothing, right, when you sum those two numbers, nothing flows from the previous digit into the next digit. So the carry in is 0. The carry out is also 0 because this digit, right, when you put 0 and 0 together, you get 0 with no, overflow. And so the carry out is also 0, and yet again, in that situation, the result is correct. So the rule is that when the carry in matches the carry out in the leftmost digit, the value is valid. You do not get an overflow. Let's see an instance where you do get an overflow. That is going to happen when you go from, say, 0, 1, 1, 1, and if you add 1, which remember, right, this is the largest positive value. If we start from 0, come all the way out to here, this is the largest positive value that we could possibly represent with 4 bits. Let's just remark that this is the number 7. And now let's think about what happens when you add 1. If you add 1, then you're going to get, right, so let's just say +1, and let's see the result, 0, 0, 0, 1. Now there, the carry in to the final bit was a 1, but the carry out was 0. There's a mismatch, right? The carry in is different from the carry out. So when that happens, this is called an overflow. And you can tell, right, or sort of consequence of an overflow is that you don't go to the representation of the next number. This is where that, right, this is basically marking the location of that discontinuity. And so this sends you all the way over to -8, right? We've said before that this 1, 0, 0, 0 represented in 2's complement with 4 bits is the representation of -8. And that, right, so going from 7, adding 1, getting over to here, that's an overflow, and it, right, in any instance where the carry in mismatches the carry out, that is an instance of an overflow. Can we think of an instance, by the way, of a situation where the carry in is 0 and the carry out is 1? That we could imagine by taking -8 plus -8, right? So this is 2 instances of -8. Clearly, throughout the first 3 digits, there's going to be no carrying, so the carry in is 0. We add these, we get 0, it goes like this, and then the carry out is 1. And so here, this is an overflow. And think about, what is going on when you take a -8 and add -8? Well, in a sense, you're starting from -8 and you're trying to step to the left because you're adding a negative number. We didn't have to pick -8. It was just a simple calculation. Even if I had done -8 plus -1, we would have gone from -8, tried to move in a sense to the left, but that's where the discontinuity is, and it sends us back, at least over to here, and because it's -8, we'd be progressing in that direction. But in any case, the point is that this is an example where now the carry in is 0, the carry out is 1, they mismatch, and that again is a sign that you're getting an overflow, that you're crossing the discontinuity of how numbers are represented in 2's complement. I guess here we're just remarking that nothing changes when you subtract a negative number. You still bit flip, set the carry in equal to 1, nothing changes. Multiplication, they're describing the same algorithm as I described a couple videos ago. Division, we know of a sort of pencil and paper algorithm for division. It looks like they're basically just showing you how the same algorithm would apply in binary numbers. It looks like this is especially an example of unsigned integers, I think, so we won't, I'm not sure how interesting that is. So let's just end it here. Already a long video.